What is strong nuclear force? First, let's start with the textbook answer. By the end, we will expand on the textbooks of the last century, but that is a good place to start. The strong nuclear force is the force holding the proton and neutron together in the nucleus. In fact, that is where the wording, strong, comes from. Very, very strong. Electrostatic force decreases at 1 over distance squared, but the funny math of that is the distances get tiny, the force become enormous. At nucleus distance, electrostatic force is huge. When proton-proton electrostatic, like kind repel, force would break apart explosively. It is called a nuclear explosion for a reason. That is electrostatic force, with that strong nuclear force disturbed. Electrostatic force will get a particle to the speed of light within 4 meters. The other part of the name is nuclear. That is the force does not appear beyond the subatomic distance. Hence, the naming nuclear. So, strong nuclear force must be more than electrostatic force at tiny separation distance when that is explosive strength. Let's show how that can happen. The picture at the right shows a helium atom. It has 2 protons in red, and 2 neutrons in purple. That is the secret, those neutrons do not, I repeat, do not have electrostatic charge, so not huge repulsion from them. There is a special 3D engineering that makes it happen. Let me explain. Below is the textbook graph of the strong nuclear force. It is shown as the purple line. It goes down to less energy up to a certain distance between particle, then it gets really positive potential. The nucleus has some huge wall stopping getting closer than 1 femtometer apart. First, and importantly, there is a red line which is electrostatic proton-proton repulsive force. Remember, like kind repels in charged particles. Strong force and that red line are the same up to a point about 1.5 femtometers. Then the electrostatic red line continues to infinite, well, that is if the protons could ever touch with that huge repulsion, which gets stronger all the way as the particle approach each other. So, basic red line, proton-proton electrostatic, ES, force is repulsive to infinity via 1 over distance squared as the distance tiny. Yet, notice that strong completely opposites attractive. The graph of the current textbook answer shows that bottom at 1.3 femtometers. For the textbooks, that is the distance where most protons and neutrons space. As you can tell, we will go beyond the textbook answer. Here is a place to start. I will critique the textbook in a number of ways that should lead to a student's easier method to understand strong nuclear force. The textbooks show strong nuclear force as the purple line, but that is the same as the red line for a large distance at the right. To me, what we are examining is not the purple line, but the difference between the purple line and red line. That difference what I will call direct nucleostatic magnetics. It is the core of strong force. That difference, my direct, NM force, is 0 at the right part. Again, the naming is quote nuclear unquote. This strong force is not material versus electrostatic beyond that distance. Please note my complaint about the purple line being a mixed number is the first way that your textbooks need to change. I hope that you will think differently about strong nuclear force than the current textbook. There will be more refinements later. So, what causes that complete reversal? At the left side of the graph, the force is hugely positive, the exact opposite of the red line. In fact, that means the difference, my refined direct NM force, is doubly larger. It is the difference from the growing negative versus the growing positive. That is direct NM. The other lines are how current quantum theory tries to explain the purple line. That is complex. Let's look at just a piece of that textbook answer by the person that won the Nobel Prize for properly predicting it. Now, this is the complex stuff, and I will explain in easier terms later. You would almost need a PhD in physics to understand how current universities explain physics, and I am truly focused to make the concept understandable. So, the 1949 Nobel Prize was given to Hideki Yukawa after the predictions for those potential at those distances from his 1935 paper were proven correct by experiment, 1945 to 1947. That formula is minus g squared times e to the minus alpha time mu time r. That is a mouthful of things few scientists understand. For example, that g relates to Planck's constant, h, not to Newton's gravity. They ran out of letters, which will only confuse a student more. The mu is the elementary particle mass. Yukawa called that a meson for, in the middle. Later, that same concept has gotten also called a pion and a gluon as the concept further developed. R is the distance to the particle. That is the one part that everyone can understand. Further, that 1 over r part is the Coulomb electrostatic potential. You know, opposites attract. Like kind repel. I went through that for only one important part. The math equation format that e to the power comes from a line integral over a known symmetry. Scientists call that e factor the exponential decay factor. However, I will take that concept further. This goes to the nature of magnetism. It is the push part of magnetism. Instead of a point charge like that Coulomb potential at 1 over r, the potential becomes that EBR format as discussed at Solvay when a force applied to an axis. Aha, magnetism.
Now, this slide explains the biggest parts of that equation that normally confuses students. First, there is a great comparison of classical physics to quantum physics. Really, the different just one layer higher. Let me explain. I think of physics equations as 3 layers. First, calculating fields at the static layer. The simple field of electrostatic is a sphere. There is a force spread out over that volume that applies to any electrostatic particle at that distance. That formula is 4/3 pi times the radius cubed. That last part is my focus. That is the volume of space that the energy spreads over. So, at any position, the force has equation format 1 over distance cubed. That is the base layer for physics. Everything starts from fields. That is the left column in the upper table. The classical physics is about force. A scientist finds all the force that arrive in one direction. That is, the field is everything in every direction, but the force eliminates one direction. All the forces directly in the line between objects. So, the 1 over distance cubed field becomes 1 over distance squared force. That is the format of Coulomb electrostatic force. That position has all the force for all the points in that same direction. So, you lose one dimension in the math formula. 1 over distance cubed becomes 1 over distance squared. That is the middle column in the upper table. Now, statistical mechanics equations work as another layer. That is the quantum theory methods. Those equations are a further integral scanning all the force at their lower impact. This time over time, but that is not important for this slide. It is another layer of integration in math. To the basic student, that is the potential is a simple 1 over the radius. That is the right column in the upper table. So, the field has 1 over r cubed. The force has 1 over r squared. And the potential has 1 over r only. All of quantum works at this third layer. However, that is more difficult. One is the integration creates a missing starting point. The same integral can yield different results. Let me explain this another way. We need to go back to algebra. We think of motion in 3 layers. Further, those are 3 layers of math integrals. You have position, speed, and acceleration. Positions and speed are easy. Yet, it took every student time to understand acceleration. That is the slope of the speed. For example, going to the top of a mount takes effort. The slope is decreasing. However, that decrease continues, but faster going down on the other side. Now, this is where the review of acceleration is incomplete. You start with lots of speed, you go up and down, the speed going up and down as you pass hill after hill. However, if you have a starting position and starting speed just perfect, decrease to 0 on the top of the mountain. At the point, the slope is 0. It will not acceleration, but for that object to stay on top, it must also have position at 0 and speed at 0, when that acceleration, slope, is 0. Now, change all that to fields, force, and potential, and you understand the basic complexity of statistical mechanics, that is quantum methods. It like rolling that ball perfectly to stop at the top of a hill. To get really advanced, then one recognizes that Newton's second law is the bridge from one set to the other. That mass times acceleration equals the force. So, in the end, physics is a 6-layer model. It is the top 3 with force as the bridge to acceleration in the bottom 3. Now, you can see how challenging it is to get equations about position and velocity, that is momentum. They are 4 layers apart from potential, all crammed into that complex equation on the previously slide. However, the work here is producing the same results, not at the potential layer, but at the force layer. The method takes an entire layer of complexity out of the challenging work. Exponentially more powerful, and easier math. Just one step to acceleration. A 5-layer model, not needing that statistical mechanics layer. That is, of course, if my method works. Wish me luck. Now, let's revisit that part of the equation, and discuss the path forward. In this slide, I compare 2 methods to obtain the strong nuclear force. The left column is the statistical mechanics method, the path of quantum theory. The right column is the force layer, which I will apply instead. Now, the rows show the different equation formats based upon the line integral settings. First, let's review the potential equations. Those are the ones used in statistical mechanics, that is quantum theory. The first row is Coulomb for electrostatic force. That is isotropic, that is spherical, the same in every direction. The second row format was used by Yukawa, he got the Nobel Prize for the strong nuclear force prediction equation. The third row is Schrödinger, which is the electron distributions. The second and fourth row were both presented by Heisenberg at the 1931 Solvay conference, but that fourth row choice has proven wrong, so I would discuss that more. The first row is the at-one-point equation. Nothing fancy. It really does not need a math integral because the force is at one point. The force calc does not change. The second row is a line integral for an inward force with symmetry to that line. That symmetry is an inward force using the Coulomb potential in row 1. It has been called screened Coulomb. Hence, the 2 parts. The over R is the Coulomb part. And the E exponent, that e to the minus something times radius is a line integral over a known domain in math. It is no longer a point force, but a force as if applied from every place along that line. That will become the basis for static magnetism. This works for the nucleus because the set connects like a chain magnet. It is on the axis, which is the same as the direct line between the particle sets. The third row is a line integral for an inward force with symmetry to a line. Again, that if the Coulomb electrostatic force. However, in this case, the orientation of that line is unknown. As such, you get that extra, I factor. That works for electrons that A, are off the axis, and B, free to rotate, or really wobble given the various magnetic fields around each electron. These make up the basis of all statistical mechanics work at the potential level. You find the 1 over R as part of each. You will find the E then exponential in both Yukawa and Schrödinger. The variance is that math I invisible number in the third row, and then in Schrödinger. Yes, by the way, I think the wording imaginary is wrong and confuses students. That is why I use invisible, it is an unknown orientation of a noble symmetry. Now, first we will finish with the statistical mechanics methods, the potential column on the next slide. I will save the replacement equations at the force level for later slides. But, that really gets to the heart of what is magnetism, that is, to me, that e exponential factor in potential, or that function of theta over distance cubed, cause of them is really the underlying static magnetism equation. However, that was not described well with the abstract potential functions. That is the heart of what explains why each of these equations works at the appropriate level. That is, you can use the quantum potential if that works better for one situation. However, you can use the force level, and that opens easier calculation for a different set of situations. Those are the one not addressed in the textbooks of the last century. The basic logic of a nucleus and strong nuclear force is an easy engineering. The main answer is spacing. That with the two forces that we already discussed. First, the huge electrostatic repulsion, the blue line, would have electrons explode from each other. Something must both A, hold them together, and B, not have electrostatic force. The answer is the neutron. The properties of a neutron include both A, having a nucleostatic magnetic strong attractive force between protons and neutrons to hold the structure together, and B, neutrons have no electrostatic charge, so not repulsion. If you put a neutron between every proton, that electrostatic force for two protons decreases. It goes down, until the repulsion is less than the nucleostatic magnetic strong force from the protons to the touching neutron. That distance is smaller. There is a little extra. A chain of magnetics keeps the same strength. That magnetic strength stays as generally a straight line along a chain of proton-neutron-proton. While the orange line in the graphic goes down, in 3D engineering, another neutron, then proton, will keep that strength. So, I think of a nucleus as a chain or ring or more complex structure, always with a neutron between every proton with 3D engineering. Now, I said that electrostatic force is huge at those tiny distances, especially if touching, that is near zero distance, so infinity squared force. However, remember magnetics is 1 over distance cubed, which is stronger by fun math of less than 1 on fractions. So, the nucleostatic magnetic strong force inside Bohr radius is greater than the proton-proton electrostatic repulsion. Yet, that only works if the protons do not touch. The separation must be stable. Let's look at this 3D engineering in the top graphic. When in a clean chain, the electrostatic force is red, and reduced. However, at the touching distance, and because it is 1/distance cubed, the direct nucleostatic magnetic strong force is larger. This is the fundamental of strong force. However, that is not the complete picture. The basic nature of magnetism is what keeps the structure generally in line. That is, the neutron, the white sphere, does not shift out of place. The force towards that axis is axial nucleostatic magnetics. That was called weak nuclear force for the last century. Of course, when the nucleons are in line, that force is zero. The system is in place. It is only as the structure gets pushed out of alignment that the weak force gets strong. The weak force just strong based upon the angle, theta, of the second particle off the axis. So, if the nucleus is alone, then that towards the axis axial nucleostatic magnetics weak force makes the structure stable for centuries. The strong force alone is the distance math, but the system does not work without the spacer, the neutron between every proton pair in 3D. In the first slide, I showed the current quantum model. However, that pictures had a pi line, a tau line, and photon line, and a omega line. It did not explain those. That is because the current textbook presentation is based upon distance, but really, you need pi and tau with the direction. The bottom drawing explains the 3D engineering approach. There is that extra purple sign function towards the axis in the drawing. That is the weak nuclear force with its 3D orientation. It's the idea that a magnetic chain wants to get back to 0 degrees, and the force pushing us back is based upon the sign of that angle. So, two things happen when the chain gets bent too much. The electrostatic gets closer, not within 1x the distance to next proton. That increases the force 4x, and the particle gets 1/2x, then the force is 16x bigger, and that overwhelms the system, and the nucleus decays. The electrostatic is still the red line at less than 1/2x distance in the drawing, and bigger. Further, because of the angle, the force offsetting electrostatic is only the projection, the hashed golden arrow. Even if the direct nucleostatic magnetic strong force is the same, it attraction force reduced by the sine of theta. That is a second factor leading to nucleus decay. So, together we have a system that is very stable by three forces. Electrostatic reduced by neutron separation. In that proton-neutron-proton chain, direct nucleostatic magnetic strong force attraction overcomes the repulsion. However, that system is held stable by axial nucleostatic magnetics weak force, which helps keep that chain in line. The system also has a way to decay any particle knocking the proton or neutron off that electrostatic repulsion of a set of particles, with each proton accelerating as 1/distance squared force over a tiny distance. A nuclear explosion strength. I spoke about that chain of proton-neutron-proton. Or maybe a ring. That seems to work great up to about 20 protons. In the right graph, you can see the relationship of protons to neutrons by elements for a stable nucleus. This is the start for understanding isotopes. The solid lines are very stable nucleus counts. The dots are semi-stable. The blank spaces are those ratios of protons to neutrons that are not found in nature. The isotope different 3D engineering where a neutron fits in between protons. In 3D, it is not only one viable structure. There are many. The system seems a chain or ring up to 20. The number of neutrons matches the number of protons. It is a 1-to-1 ratio, which you can see as the red dotted line extending beyond the places where it has the solid lines, that is the stable nucleus ratios. Above 20, the system requires extra neutrons. That ratio increase until after 210 nucleons. In the second radioactive range, the ratio is 3-to-1. That is the 3D engineering of a triangular pyramid. With that, the elements by proton count and isotopes adding neutron count begin to look like 3D engineering. The abstract counts of the current textbooks get replaced with straightforward 3D mechanics. The graphic at the right was produced by J. D. Van Bell. He does a great job of putting abstract quantum theory into a more understandable presentation. In this graphic, Van Bell compared the strength of Coulomb potential, which the red line for electrostatic force, and the strength for the Yukawa potential, which the blue line for strong nuclear force. The shape is different. Both are decreases of distance, but the strong force decreases exponentially more. A potential that is the 2 formula. However, as forces, this is 1/distance squared versus 1/distance cube. More importantly, Van Bell showed that these two forces have an equilibrium at alpha. That the electrostatic is stronger beyond, and the strong force is weaker inside. However, that is not that 1.3 femtometers. That is the Bohr radius, which is 10,000 times larger. That is the level of where the electron shell lives. So, with that you have all the traditional strong force to the nucleus. However, remember that above graphic, because that is the rest of the lecture. That is application of the strong nuclear force for an equilibrium at the Bohr radius. Now, the current presentation is that the mass of the elementary particle is a meson per Yukawa. Not, that naming has changed to pion, as in the pi in the first slide, and to the gluon, as what glues the nucleus together. That particle in the standard model has the mass between the mass of a proton and the mass of an electrons. That is why Yukawa chose meson, with the meaning in the middle. Those masses show the table in the upper right. However, it is much closer to the proton mass. It is 200x compared to the electron, but only 9x compared to the proton. The current textbook uses mass as the means to distinguish acceleration. All forces are calculated as electrostatic. So, by Newton's second law, the acceleration is force divided by the mass. So, that method changed the mass, you change the observed results in 3D. Position, velocity, and acceleration. When the predictions do not match the experimental results, but have a consistent results, a new elementary particle is declared with the mass to the electrostatic force divided by that equals the consistent experimental acceleration. A new elementary particle of mass x is declared. I have worked for the last half century. Yet, I will take a different approach to get to the same experimental results. I got back to that comparison of force strength for nucleostatic magnetics. That strength has a different provided than electrostatic. So, I get the same results by A, using the 1/distance cubed force profile, and B, finding the 3D distance and orientation. That combination uses the equations of electrostatic, strong and weak, and then each event with a separate elementary particle with its mass, gets replaced with one of the three force and the settling distance. The graphic in the center is the key to understanding both elementary particles and the replacement system here. As I already stated, the subatomic world has an axial force that orients towards the second particle axis. In this graphic, that is the brown hashed line. It has a line from particle 1 to that axis. That closest approach is always at 90 degrees, so orthogonal to the axis direction. That creates a distance between particles of r. Yet the distance to the axis closest approach must be some distance less. I label is r sub p for the perpendicular. That will become the distance to the effective strength of that configuration. For the strong force, that ratio has the same relationship as the table in the upper right. You see, the second particle is the net of a proton at 1 diameter and the next neutron after that is 2x the distance. The proton separation is 2x the neutron diameter. That only happens when you calculate based upon the 1/distance cubed and the 1/distance squared. The distance of a nucleon to a nucleon is about 1.3 femtometers. Both fields are extremely strong at that separation, that is, the mass is huge. The distance for the strong force is double because it's the proton-neutron-proton or neutron-proton-neutron chain spacing. So, the field gets decreased by the doubling. A quick ratio of the cube of 2 is 8, which is near the 9 in the table. That is why the observed mass is 8 to 9 times smaller. The position in that combo field is less, so the observed strength is the magnetism unshaded. However, the electron is at the Bohr radius, which is far away, and that gets mass of the electron. The magnetism is not shielded to the extent that the first particle intercepts the axis of the second particle. That is the variance between R and A as per Van Bell, but also, not in Van Bell, the variance between R and R sub p. That is the 3D engineering of mass shielding. Much of chemistry requires understanding that observed mass changes with bonding. That rest mass then changes. That is all about the relative axis intercept and the Bohr radius. The force calc is based upon the closest approach, and since the axis goes in two directions, that is a magnetic duopoly, that closest approach is always closer. Well, or equal if the axis goes through the second particle. I will replace the elementary particle mass with the axis closest distance. This concept is key to each force replacement to the quantum potential equations of the textbooks for the last half century. So, the understanding of strong nuclear force is about a 1/distance cubed direct nucleostatic magnetics force. The teaching of the last century that we have A, electromagnetism with B, strong nuclear force with C, weak nuclear force mixed up the terms. The challenge is that static magnetism is the B, strong nuclear force with C, weak nuclear force. That leaves the A, as electrostatic force only. That is the same solution mathematically, but with 3D engineering to explain it. That means that the strong and weak force are the combination that keeps the nucleus together, when proton-proton electrostatic repulsion should cause nuclear decay and explosive repulsion. Now, I could compare this to the pi and the tau of the original textbook graphic. That math works. But, I won't. However, I would rather explain how this electrostatic, strong, weak model also solves the other major problem with last century atomic model. Electrons fall into the nucleus. It is a fundamental failure of the current textbooks. Importantly, the strong nuclear force, as direct nucleostatic magnetics, actually solves that problem as well. With the same formulas, and with the added benefits of 3D engineering. So, strong nuclear force with electrons. Onward? Now, the introduction of strong nuclear force with electrons. The current textbooks of the last century only discuss the strong nuclear force as related to the nucleus. So, this is beyond, and not yet agreed by all scientists. One would think that the force does not apply beyond that distance. Certainly, that graph seems to stop at 1.3 femtometers. However, that is an incomplete picture. That is just the nucleus. In the case of electrons in their fields or shells, the 3D engineering is different. In that interaction, the electrostatic of protons is offset by the electrostatic of nucleus protons. So, the electrostatic forces is gone. That is important. Electrostatic is gone so long as electrons stay in a field averaging the Bohr radius, with a Pauli hemisphere adjustment. In fact, the 1935 paper that led to Yukawa's Nobel Prize, stated that the strong nucleus force applied to heavy particles, that is protons, and to light particles, that is electrons. Yukawa understood that the force was not just in the nucleus. However, Yukawa's potential equation did not work because electrons are not on the axis, so weak force applies as the inclination angle is not zero. Hence, you need the E9 version, which is Schrödinger's equation. Yukawa tried his formula and failed. I know that your textbook does not mention strong force with electrons. However, it is the most critical part of an electron field. The rest of the slides explain that relationship. For most people, magnetics is that iron filing shape. That big at the equator, and scrunched at the poles. So, with this model of both strong and weak force. This explains that shape based upon the two force vectors. The direct nucleostatic magnetic strong force is just that. It is in the line between the particles. That means that the repulsion pushes the system outward. That is the wide part at the equator. There is the large direct strong force. The weak force is immaterial at the poles, but that calculation is in a separate lecture in the weak force series. It is small, but back toward the axis. So, the weak force is toward the axis. So, if the particle position is beyond the end of magnet, then those inward force pull it back to the pole. That creates the scrunched inward polar shape. Now, the math of permanent magnetics includes particles at one end, and at the other, to the net effective is that pulled towards the center of the permanent magnetic set of molecules. That makes the effect more pronounced. For this lecture, we are focusing on one atom, and one nucleus, so the scrunch is not as pronounced. The towards the axis is a drop perpendicular, that is not inward. However, the shape of the atomic system static field has that wide as the equator feature. So, strong and weak force are not separate from magnetism. Those are the two parts that together create magnetism. Let's review that change to the textbooks of the last century. Strong and weak force are not separate from magnetism. Those are the two parts that together create magnetism. The prior model had electrons handled by a combination of electromagnetism. The nucleus was handled by electrostatic, strong, and weak force. Further, there is a time-dependent counterforce when the fields change based upon Lorentz. Finally, there is a totally separate gravity. The model here is cleaner. For the nucleus, you have the electrostatic force, the direct nucleostatic magnetics, strong nuclear force offset that. It is in the same line, but with opposite sign. The axial nucleostatic magnetics, weak nuclear force holds the particles in that chain proton-neutron-proton. For the electrons, you have the same three with the same equations. The electrostatic force. The direct nucleostatic magnetics, strong nuclear force offset that. It is in the same line, but with opposite sign. The axial nucleostatic magnetics, weak nuclear force holds the particles which cause the initial shell 1-2 poles, so 2 electrons then full. Then it creates the hemispheres, and the subshell sets a specific inclination angles of the same energy, and the spacing of those in hemisphere pairs of 2, 6, 10, and 14. It is fantastic to use the same equations for nucleus reactions and for electron reactions. Further, the same equation also solves gravity. The electrostatic is 1/distance squared, and the other two are immaterial after a certain range. I have a separate lecture on that calculation. Of course, this also has a time-dependent counterforce when the fields change based upon Lorentz. When complete, this will handling all static with the 3, and the 1 extra for time. This is a huge consolidation of the work that the textbooks of the past century has explained as separate. In 2017, Arno presented the force graphic here of this balancing of electrostatic and direct nucleostatic magnetic strong force. It matches the force version to the potential graph of Van Bell. However, it was earlier and applied to electrons, not nucleons. It is the same Yukawa equation, but as a force vector equation, not as a quantum potential equation. Van Bell's work parallels Arno's. Yet, this graphic makes the electron shell equilibrium much easier to understand. It has the third green net-2 force combination that is not in Van Bell. The electrostatic force is red, and it goes to negative infinity. That is the why don't electrons fall into the nucleus important question about the fuzzy ball. The force is physics negative, which is attractive. The negative means the object acceleration is reducing the distance, hence the negative sign. Similarly, physics positive is repulsive. The acceleration changes feed towards increasing the distance. Hence, positive. The direct nucleostatic magnetic strong force is the Newtonian opposite. Physics positive. However, its slow is 1 exponent steeper. It is 1/distance cubed. That creates the direct line self-sustaining equilibrium. The green line, the net-2 force, has two properties. First is has a zero position where the push and the pull balance. However, unlike in the nucleus, that is a downslope through zero. The electron, if the distance gets smaller, has a physics positive repulsion. That pushes the electron back to equilibrium. The electron, if the distance moves further away, has a physics negative attraction. That pulls the electron back to equilibrium. One does need the neutron for a system of free separate partials. The Bohr angular momentum model gets replaced with a net-2 force of electrostatic always offset by direct nucleostatic magnetic strong force. Many students prefer this presentation. This is a 2D slice with the force as the up or down z dimension. The above includes the electrostatic force, the direct nucleostatic magnetic strong force, and the axial nucleostatic magnetics weak force. It has the 1/distance squared attraction and the 1/distance cubed repulsion. That creates a wall where electrons will not fall into the nucleus. However, this also has the pull to the poles, so there is a valley at each pole where the first 2 electrons prefer. That is O1 hydrogen, then O2 helium, the shell 2 is full. The 3D engineering of the 2 everywhere in chemistry. This model expands to explain the periodic table of elements and chemical properties based upon 3D engineering of the nucleostatic magnetics vector equations. Since I mentioned the nucleostatic magnetics vector equations, I will end the lecture by showing them. These are forces in a hemispherical coordinate system, the same as the quantum numbers. The r dimension is the layers, the direct distance between particles. The theta direction is the inclination angle, or longitude. That is the direction towards the poles, which is towards the axis, but adds the factor of being at 90 degrees orthogonal to the radius dimensions. The phi direction is the latitude spacing. That is at 90 degrees in the short range to both the radius r and the inclination theta. The orange arrow highlights the direct nucleostatic magnetic strong nuclear force. That is only in the r dimension, just like electrostatic force. The equation is similar to the Coulomb electrostatic equation. However, the K needs the A added for that self-sustaining equilibrium as the Bohr radius. That is the same A as in the mu times A in the Euclid potential version. I have run out of time. Sorry, this was so long. Thanks, and big hugs.